All right, so what we have here is what we have here is the graph of a function. I'm moving over the graph of a function. Um, this is the graph of the function, let's say, f of x. All right, so here's the graph of the function f of x. I'm moving right over it. This is the y-axis. This over here is the x-axis. So here's the graph of this function. This over here is the graph of the line y equals 1. This is the graph of the line, let's say, um, x equals d. Okay, here's the point d. This is the point O. This is the point here, E, and so forth. So, so what are the questions that can be asked about this graph? Suppose that you were given this graph and ask, and suppose that M here, let's say, suppose that this point M in the x-axis occurs where the asymptote, sorry, not the asymptote, where the tangent line here is horizontal. This point A occurs with a tangent line here. Okay, the tangent line uh, here is horizontal. Okay, suppose that that is the case. Suppose that the point M here occurs with a tangent line here is horizontal. Okay, suppose that the point, let's say, let's call this point here, I'm going to call this point here, let's see what I'm going to call this point right over here. I'm going to call this point, let's say, omega. I'm going to call this point over here omega. Okay, so suppose that this part of the graph here occurs, the point omega occurs at exactly the x point, the x value where, okay, where the tangent line here is horizontal, right? Suppose that is the case. And let's say this is the point O here. Look what's happening here. We have a horizontal tangent line, right? And so let me actually, I was going to make this, I'm going to make this a sharp beak. I don't like the way it looks. I'm going to make it a sharp beak here, okay? So I'm going to be asking you questions about this graph in a little while. So let me make this into a sharp beak using, let's say, black. I'm going to make this into a sharp beak here using black. Let's see, I don't like the way it looks. I'm making it into a sharp beak. Okay, so here I have a sharp beak. And I got this sharp beak. Okay, so my pen here. Okay, so let's see. Okay, so this sharp peak occurs right over the x value e. Okay, so everything is quite smooth. This is not a sharp peak here. This is just a very nice rounded edge. Okay. So let's see what we're going to be talking about now. Okay, let me erase this over here. I don't need this y equals 2 there, right? I'm going to erase this here. This is unnecessary information. So let me ask you some questions about this. Okay, so I'm going to be asking questions about this graph, right? So the first question is that I'm going to be asking about this graph Let me make this nice and rounded here. Nice and rounded, not a Sharpie. So I'm doing a nice and rounded graph there. I'm having a hard time doing this. All right, so my question is, let me ask you some questions here. Okay, so I'm going to take, this is the line x equals d. So this smooth, nice, okay, uh, graph here is the graph of the function f of x, which is an expression of x. Okay, sharp peak, then you know the graph looks really nice. Excuse the fatness of this graph here, but it's just a line. Okay, and all right, so the first question that I'm going to ask is find the limit of as x approaches, let's say uh, d from, let's say, from the left. Okay, from the left, look at that, of f of x. What is the limit of this as x approaches d? This is the value d here, look at that, from the left. In which direction is it going to go? Well, obviously, this is a vertical asymptote here, okay? So this is going to be equal to negative infinity, right? So this is going to be equal to negative infinity. And so that's what it equals, negative infinity. Negative infinity. Now let me take the limit. I'm going to find the limit as x approaches, let's say, as x approaches, I'm taking the limit as x approaches d from the right, okay, of f of x. Let's see what that is going to be. I'm approaching d, this value, x equals t, and I'm approaching from the right. Now look at the graph, look how the graph is behaving. The graph is actually, this is equal to infinity. Okay, so positive infinity. As you approach d, this is the value d, as these are the x values, so as x approaches d from the right, this graph is moving to positive infinity. It's not really stopping here. I basically stopped it because I couldn't draw it closer, but it's actually moving closer and closer to this vertical asymptote x equals d. So another question is, so let me ask another question. So does the limit as x approaches d exist? So it goes from negative infinity. So question, does the limit as x approaches d exist? And what is the answer? No. The limit does not exist because it is infinity. And if you approach it from the right, it is infinity. If you approach it from the left, it is equal to negative infinity. So it doesn't exist. This limit does not exist. Question, is the function differentiable at the point x equals e? Well, at the point x equals c, the function is clearly not differentiable because you have a sharp beak. Okay, so this is definitely, so f of x is not differentiable at x equals e. Why is that? Well, let's look at this situation. Look what's happening at x equals c. We have this sharp beak, so the function is certainly not differentiable there, right? Let's see. Now this is this red line y equals 1, okay, of this function. So this function f of x looks like a rational function of sorts. So let's see the limit as x approaches infinity. So the limit, so let's actually compute the limit. Okay, let me actually erase this. So I'm going to compute the limit of this function. So limit as x approaches infinity of f of x. Well, let's see what is going to happen. This is, as you move to infinity, this function, the graph of this function, this is the graph of f of x, seems to be becoming a line y equals 1. Okay, so it's moving to infinity here. So this is equal to 1. Okay, now actually, no, to make matters more interesting, I'm going to make this function go to infinity. Okay, I'm going to make this function go to infinity here on this side. So let me find the limit. Okay, I'm going to find the limit of f of x, right, as x approaches negative infinity. What is it going to be equal? Actually, this function seems to be going to infinity. It's going to be infinity. Okay, as you approach negative infinity, this function is, by what I just did, tending to infinity. So it's going to infinity on the left side. As you approach infinity on the right, okay, positive infinity, the function moves closer and closer, closer and closer to the line y equals 1. Okay, so the limit is 1 there. Okay, so let me actually make this a little bit more, make it a little nicer. It doesn't make that nice. So let me make this infinity. Okay, so now what I want to do is I want to test question. What is this over here is the graph of the function. Over here we have the graph of the function. Let me actually ask you a question. What is the first derivative of the function positive or negative at b? Question. Is first derivative of the function is f prime of b a positive value, positive, or negative? Well, is it positive or negative? Now look at this value b here. Now this function here is increasing. So what is it going to be? Answer: positive. Okay. Now let's see what's going to happen over here. Let's see what's going to happen over here. Look at this stuff here. It looks like it's concave up. Question: is f double prime at b positive or negative? Is f double prime of b positive or negative? What is the answer? Well, look at this stuff over here. It looks like this is concave up versus concave up. Let's remind ourselves of what concave up is. Concave up, concave down. Okay. So the function seems to be concave up here, right? So this seems to be concave up, this function right over here, right? So this over here will be, that's the question, so it will be answer positive. Okay, let's see what else we can say here. Okay, so let's look at a value here. I said this was omega. Let me make it in black. Let me make it black over here. Okay, so I'm going to make this black. I'm going to make this value here omega. I'm making this value black. Okay, so let's see what happens here. This is omega. Okay, so question: is the first derivative at omega of the function 0 or not 0? Now let's see. This omega is right above here where the tangent line is horizontal. Okay, so the answer is, because the tangent line at this point here, okay, over omega is horizontal, we know right away that the derivative, the slope of a horizontal tangent line is going to be 0. Okay, so this over here tells us that f prime of omega, okay, is going to be equal to 0. Right? So f prime of omega is going to be equal to 0. Now let me ask another question. Let's say that this point over here, okay, so this point, this point over here, right over here, corresponding to this. So question, what is f double prime at O? This is O here. It looks like really weird, but it's I meant it to be O. Okay, so this is O. Let me write this here. Okay, that's O. So what is f double prime of the letter O equal to? Is that positive or negative? Let's say positive equals positive, or let's say, let me write this by hand, equals, let's say, is equal to positive, or let's say negative. Explain. Okay, well, let's see. This is O over here. Now, if you look at f double prime here, this is concavity. Okay, so f double prime is going to be of O is going to be positive. Question: what is O? I mean, assume that the horizontal tangent, the tangent line at O over here of this graph was horizontal. The question is that a local maximum or a local minimum? Answer: it is a local minimum because f double prime of O is positive. So by the second derivative test, it's going to be a local minimum. All right. So let's see what else we can ask here. Okay, let's see what we can ask. Okay, so now E is where the graph has a sharp beak. So question. Let me ask this question. So what is the limit, okay, as delta x, let's say as delta x, okay, it has a sharp beak here. Let's see what I can ask. I'm going to try to ask a question. So what is the limit as delta x approaches, that's doesn't look right, that doesn't look like approaches, okay, approaches, let's say, 0 of f of, let's say, f of E plus delta x minus f of E, divide this whole thing, okay, I'm going to divide this whole thing by delta x. Does it exist? Does it not? Well, I'm taking, when I do the limit as delta x approaches 0 of f of E plus delta x minus f of E over delta x, theoretically, I should be getting the derivative, but this has a sharp beak right over here. Look at that. We have a sharp beak right over here. So as I'm approaching this limit, there is going to be no derivative. So the limit of f of E plus delta x minus f of E over delta x, the question they might ask us, does the limit exist? Does this limit exist? Okay, so question, okay, so they want to be nasty, and they're asking us, does this limit exist? Does this limit exist? Let me move this a little bit to the right so that you can see. They're asking me that question, right? Does this limit exist? Well, obviously, the limit is not going to exist because if it did exist, it would give me the derivative, okay, at the point E, x equals E of the function f of x. So it cannot exist. So this answer, no. This limit cannot exist. This limit cannot exist. Okay, so limit cannot exist. Okay, so limit cannot exist. Limit can't exist since the function is not differentiable at x equals c because it has a sharp beak. Since not differentiable at x equals e. Okay, so that function is not differentiable there. By the way, is the function differentiable at x equals d? Question. Question. Is f of x differentiable at x equals e? I'm sorry, not x equals c. Let's see what this value is. X equals d. This is what that vertical asymptote is. So let me make this d over here, right? So is the function differentiable at x equals d? And the answer, of course, is not differentiable at x equals d, because if you, as you see, you're having a vertical asymptote, okay, at x equals d. In fact, if you approach the point d from the left, the function goes to negative infinity. If you approach it from the right, it goes to positive infinity. So this function is not even continuous at x equals d. And remember that for a function to be differentiable at a point, it has to be continuous there, right? So functions cannot be differentiable at points that they're not continuous. Question: is the function f of x continuous at the point x equals c? Well, yes, it is. You can draw its graph without lifting your pen. It is not differentiable at x equals e, but it is continuous because you can draw its graph without lifting the pen. Okay? Let's see. Let me see if I can find a place where this function is concave down. Well, okay. But it looks, in my head, it looks, okay, like this function is concave down to me. It looks like this function is concave down right around here. Look at that, because this looks concave down. See that? Right over here. So let's say at this point, suppose that this was the point, let's say t over here. The function seems to be concave down at the point, let's call this point over here. I'm going to call this point t. Okay, so it seems to be this point, let me call this point t. Okay? This seems that the function is concave down at the point x equals t. In other words, if you were taking the derivative of this function looks like it's, concave down. Yeah, it's concave down. So it looks like it's concave down at the point x equals t. So if you took the double derivative of this function and evaluated it at t, what would you get? You would actually get a negative number. Okay, so let me erase this here because I don't need that. But, okay, so that's the story. Question: is this function increasing between, let's say, b and let's say c? Question: is f of x increasing between b and c? Let me erase this over here. I don't need this over here anymore. I'm going to be erasing this. Question: is f of x increasing, okay, let's say between b and c in the interval, let's say, let me make it an open interval, b and c? What is the answer? Of course it is. If I were to take, derivatives of this function and compute tangent lines, they would all be pointing up between b, this is b, and c. They would all be pointing up. Therefore, the function would be increasing. So what does that mean? It means that the derivative is positive. So someone could have actually asked me, so let me actually write this, let me write the answer to this. Yes, yes, it is increasing. Yes. In fact, you can actually easily determine by drawing tangent lines to this function on the interval between b and c that all the derivatives are positive because the tangent line point up. They are increasing. Yes, so it is increasing between b and c. Now, is the function decreasing, let's say, under on the interval, let's say between e and infinity, between e, this is e, and infinity. So question, let me erase this over here, or maybe let me write it over here. Is f of x decreasing in the open interval? I'm going to choose the interval e to infinity. I'm going to choose in open interval e to infinity. So they're asking that. Well, e to infinity. This is the value e here. Look at that. That's e. Now I'm choosing an open interval. So is it decreasing between e and infinity? The answer is yes, it is. This function is decreasing because if you were to compute uh, the derivatives, the tangent lines, okay, would all be pointing down as you move along here, along the graph of this function. So they will all be pointing down. So the function obviously is decreasing between uh, e and infinity. Okay, so yes, it is. Answer, yes. Okay, so the answer is yes. Yeah. Okay, that is the case. All right, so you have a very good idea then, if you understood what I said, of what's going on here. Okay, you have a very good idea of what is going on here. And these are very nice things to ponder as you prepare for a final exam in Calculus 1. Thank you for listening.